Hello, student. Uh, Welcome back to this topic of perturbation theory. So, this perturbation theory is a branch of quantum mechanics, and this perturbation theory is developed because the Schrodinger wave equation became inadequate to solve some of the problems. So because of that reason, this perturbation theory is developed. So we'll see what is this perturbation theory, or first we'll see what is the meaning of this perturbation. A small change in the Hamiltonian of the system is called a perturbation. So you know the Hamiltonian in quantum mechanics depict a physical system, or it describes a physical system, and all the energy values are defined for this Hamiltonian. And when there is a small changes in the energy value or some other parameters associated with this Hamiltonian are changing, that we say that there is some perturbation. So it is also referred as a small disturbance in the Hamiltonian of the system. So this small disturbance in the Hamiltonian of the system may be in any one of the parameters which are associated with the Hamiltonian of the system. So that is why this Hamiltonian is very, very important. So that it depicts or describes a physical system in quantum mechanics. The Hamiltonian of the system is generally given by this equation. This Hamiltonian is equal to T plus V, where this T is the kinetic energy of the system, and this V is the potential energy of the system. So that is why the Hamiltonian actually it represents the total energy of the system. That total energy is comprised or composed of kinetic energy and potential energy. That means a part of the total energy is kinetic in nature, and the remaining part is the potential energy. So if there is, for example, if there is a small disturbance or change or variation in the potential energy of the Hamiltonian, then we can say that there is a perturbation. Or if the kinetic energy changes by a small amount, then also we can say that there is a perturbation. So most of the time we are concentrating on the variations in the potential energy of the system. So this is the meaning of perturbation. One of the parameter will be slightly changing from its average value or the constant value. Then generally we say that there is a perturbation. The potential energy, the potential barrier for a symmetric wave function is shown like this, because I am going to explain you how the potential barrier of a system with perturbation is shown schematically or pictorially. So the potential barrier of A symmetric wave function. Symmetric wave function means when the states are exchanged, then there is no change. That kind of wave functions are called as the symmetric wave functions. So a symmetric wave function is shown like this. It is a potential barrier. So this A value, this is the width of the potential barrier. It is increasing in positive x direction or negative x direction in two dimension. So the height, the infinity, this vertical axis or y-axis indicates the height of the potential barrier. So here we have shown this as infinite. The height is indicated here as infinite. The meaning of this is that this is a potential barrier of infinite height. So here the height of the potential barrier is infinite. So that is the meaning. So the potential barrier for a symmetric wave function is shown like this. So this is for unperturbed system. This is for unperturbed system. So there is no perturbation for right now in this case. Next, the potential barrier for a asymmetric wave function or system is given by like this. It is shown like this. The difference between the symmetric and asymmetric potential barrier you can see here. It takes the asymmetric wave function takes only the positive value, or it may take only the negative value. Both positive and negative value will not be taken by this system. But here, the symmetric wave function can take both the positive and the negative values. That means it can expand in either way, either in positive direction or in the negative direction. So this is the potential barrier for the asymmetric wave function without perturbation. So the potential barrier for asymmetric wave function or a system which has a small perturbation is shown like this. So this potential barrier is shown for asymmetric wave function. And you can look at the bottom of the potential barrier. When you go from 0 to A, when you are at A by 3, the potential suddenly rises. So when you are moving along this line or along the x-axis, the potential barrier should be 0. But when you reach the point A by 3, the potential barrier, the potential at this point rises to V0. Then it remains constant for some time and then it comes down. So this rise in potential at the middle of this potential barrier is referred as the perturbation. Is referred as the perturbation. That means when you are in this range of this A value, the potential energy of the system changes. So this we said that the perturbation exists in the system. So this is how you can see here. There is no potential rise in between 0 and A. But in this case, there is a potential rise at the point A by 3 and it comes back at A by 2. So this happens only when there is a perturbation in the system. As I explained earlier, perturbation refers to a small change in the potential energy of the system. Sorry, this page is repeated here. So next, here I will show you just for your reference The solutions of a unperturbed system are a potential barrier for asymmetric wave function. This is a asymmetric wave function, are given by psi n raised to 0 is equal to root of 2 by a sine of u phi by x by a, and en is equal to u square phi square h cross square divided by 2m a into square. So these two are the solutions obtained by the Schrodinger wave equation. These two are this is the eigenfunction and this is the eigenvalue. These two are obtained by applying the Schrodinger wave equation for this asymmetric wave function. But when for the asymmetric wave function without perturbation, when the perturbation exists in the system, we cannot apply the Schrodinger wave equation, or the Schrodinger wave equation will not give the complete solution or the exact solution. So that is why we have to do it in some other way. So generally, the solution of an unperturbed system are used to get the solutions of a perturbed system. So the solutions of an unperturbed system are used to get the solutions of perturbed system. So what is the idea or technique here in studying a perturbed system is that first we have to study the perturbed that Hamiltonian of a system using this Schrodinger equation, which are applied to the unperturbed part of the Hamiltonian, and its solutions are obtained. And those solutions are used to solve the or to get the eigenfunction and eigenvalues for the perturbed system. So this is how a perturbation theory is applied to a physical system. Next, we will see what are the types of perturbation theory. So there are two types of perturbation theories. One is time-independent perturbation theory. Another one is time-dependent perturbation theory. So two types of perturbation theories. So in a time-independent perturbation theory, this h dash is not equal to h dash of t. That means perturbed h dash is not a function of time. So the total Hamiltonian of the system is represented as h is equal to h naught plus h dash, that I have not written here. The total Hamiltonian of a system is given by h is equal to h naught plus h dash, where h naught is called as the what is that? The Hamiltonian without perturbation, and h dash is called as the Hamiltonian with perturbation. So this Hamiltonian with perturbation is represented as h dash, and if this h dash is independent of time, if this h dash is independent of time, then it is called as a time independent perturbation theory. Here, the time dependent perturbation theory, so this h dash means the Hamiltonian of the perturbed system depends upon the time. It depends upon the time, and hence this is called as the time dependent perturbation theory. So here the Hamiltonian of the perturbed part depends on time, but here the Hamiltonian of the perturbed part independent of time. So accordingly, we are getting two types of perturbation theories. Examples for time independent perturbation theory are H dash is equal to V naught, and where this V naught lies between A by 3 and A by 2. H dash is equal to G cos X, or H dash is equal to delta X minus A. So these are the examples of the Hamiltonian for perturbed part. So you can look at this, all these three examples. What is clear is that there is no time involved. Here is dash in all these three cases. The H dash is independent of time, and hence they refers to the time independent perturbation theory. But in this example, we can see examples for time dependent perturbation theory. H dash is equal to V naught cos omega t. H dash is equal to V naught sin omega t. So that means here, this H dash, which is the Hamiltonian of the perturbed part, depends on times. Omega t, t is the time here. So here also it depends upon time, and hence these two are the examples for time dependent perturbation theory. So there is another way of classification for time dependent perturbation theory. So this time independent perturbation theory is again divided, means subdivided into two types. So this is time independent perturbation theory. Two cases arises here. One case, non-degenerate case. Other case, degenerate case. So one is the non-degenerate time independent perturbation theory. Other one is the degenerate time independent perturbation theory. And let me explain what are these two. So this non-degenerate perturbation theory, this applies to a system where the unperturbed Hamiltonian have non-degenerate eigenvalues. So be careful here, it is H naught. As I told, H is equal to H naught plus H dash. H is equal to H naught plus H dash. What is H naught? Unperturbed part of the Hamiltonian. What is H dash? Perturbed part of the Hamiltonian. So these two makes the total Hamiltonian, and this applies to a system where the unperturbed Hamiltonian, this H naught, unperturbed Hamiltonian H naught have non-degenerate eigenvalues. So here we have written the Schrodinger wave equation for time independent case. Three examples are there. H naught psi 1 is equal to E1 psi 1. H naught psi 2 is equal to E2 psi 2. H naught psi 3 is equal to E3 psi 3. So this is the Hamiltonian H naught of the unperturbed system. And psi 1, psi 2, psi 3 are the eigenwave functions. And E1, E2, E3 are the eigenvalues. So we can see here is that this Hamiltonian of the unperturbed part is having different energy values, eigenenergy values. So, and hence this is called as the non-degenerate eigenvalues. These are called as the non-degenerate eigenvalues. That means each eigenfunction have different eigenvalues. Each eigenfunction, psi1, psi2, psi3, these are the eigenfunctions, and these have the different eigenvalues, E1, E2, E3. These are the different eigenvalues. So this is the case of what is that? Non-degenerate perturbation theory. So degenerate perturbation theory, that means degenerate time independent perturbation theory. This applies to a system where the unperturbed Hamiltonian H0 have degenerate eigenvalues. So in this case, this Hamiltonian H0 have degenerate eigenvalues. So examples are here. So this is the time independent Schrodinger equation. So H0 psi1 is equal to E1 psi1. H0 psi2 is equal to E1 psi2. H0 psi3 is equal to E1 psi3. So eigenfunctions, different eigenfunctions have the same eigenvalue. Different eigenfunctions, psi1, psi2, psi3 have the same eigenvalues, E1, 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 and hence this is the case of degeneracy. This kind of wave functions are called as the degenerate wave functions. Yeah? This kind of wave functions are called as the degenerate wave functions, or this is also called the phenomena of degeneracy. The phenomena of degeneracy. The phenomena of degeneracy means the different wave functions will be having the same energy value. So this is the case of degenerate perturbation theory. And hence we are coming across these two kind of what is that? Time independent perturbation theories. So one is non-degenerate perturbation theory, because here the unperturbed Hamiltonian H0 have the degenerate eigenvalues. That means different eigenfunctions have the different eigenvalues. And another case is the time independent degenerate time independent perturbation theory, where the unperturbed Hamiltonian H0 is having degenerate eigenvalues. So two cases are arises. And the next point is that when we can apply the perturbation theory. So the perturbation theory can be applied only when perturbation term H0 should be small. The question comes here, whatever may be the perturbation value, can you apply it or can you study it? No, because only the small variations or deviations from the Schrodinger equations are only could be studied. If there is a drastic change in the values from Schrodinger equation results, then you cannot apply the perturbation theory. So therefore, this perturbation term H dash should be small enough, then only we can apply the perturbation theory. Then second point, by making use of the perturbation theory, only approximate solution of a system can be obtained, but not the complete solution. So this perturbation theory is not giving the complete solution or the exact solution. So the exact solution or the complete solution is the one which is obtained by applying the Schrodinger wave equation. As I told initially, the Schrodinger wave equation is not applicable to the systems which are having the perturbation. So that is why this perturbation theory gives only the approximate solution of a system, but not the complete solution. So if you want the exact solution, you should apply this Schrodinger equation only. So that is why a solution obtained by solving a Schrodinger equation for an unperturbed system is called the exact solution. And the main important point is that these Schrodinger equations are not suitable for studying the system which is having a perturbation. So that is another important point. So here are some results. Time independent perturbation theory for non-rigid energy levels. Just I will go through these some results. And as I told, the total Hamiltonian of the system is given by H is equal to H naught plus H dash. And this H naught is the Hamiltonian of the unperturbed system. And H dash is the Hamiltonian of the perturbed system. And the energy eigenvalues are given by this equation like this. So these are the eigenvalues. So En is equal to En0 plus En1 plus En2 plus dash 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 dash. So the 0, 1, 2, 3 represents the first order, second order, or the states for that particular state. So here En represents energy eigenvalue for the perturbed Hamiltonian of the n state. So it is the ground state, this is the first excited state, this is second excited state, like that. And En of 0 means energy eigenvalue for unperturbed Hamiltonian of the n state. And En of 1 means it is the first order energy correction term for the energy eigenvalue of the n state, or it is called as the first excited state. So that is represented as En of 1. And this psi n, it is in a direct notation. This is a ket psi n. So ket of psi n is the energy eigenfunction for perturbed Hamiltonian of the nth state. And similarly, this psi n of 0 is the energy eigenfunction for the unperturbed nth state. This is for the nth state. And this is for the first excited state or the first order correction. So in this case, the energy eigenvalue and energy eigenfunctions for unperturbed system are given by this equation. These are actually obtained by applying this Schrodinger equation. As I told initially, in the perturbation theory technique, first we have to get the solutions for unperturbed Hamiltonian by applying the Schrodinger equation. So these are the eigenvalue and eigenfunction equations obtained by applying the Schrodinger wave equation for the unperturbed Hamiltonian. This is studied in earlier chapters. So the first order energy eigen correction is written in this way. It is written in matrix form. Psi n h dash psi n is h dash. So this is the first order energy correction for the perturbed Hamiltonian h dash. Actually, these are to be derived, but I am not going for the derivation. Just I am showing the results. So the second order correction for this perturbed Hamiltonian h dash is given by like this: En of 2 is equal to summation m is not equal to n, and because these are the asymmetric wave functions, so h dash is equal to psi m and psi 2 is two states are there, m and n, matrix square divided by en minus em, and the corresponding wave function is given by this equation. So these are the basics of perturbation theory. And next, I have to consider the time dependent perturbation theory, uh, which is there for your syllabus. And already I have made a video for this, and you can go through it. So thanks for listening.